Hey, welcome back to a new week, advanced or pre-calculus students. Let's get ready for our first video of the week, which is going to be on infinite series. It's finishing up 9.4, so we started 9.4 last week, where we talked about what series were, and we talked about how to use the summation notation to write them. And now what we're going to talk about is particularly focus on the infinite series, and what we're really going to focus on, particularly within the infinite series, are convergent infinite series. In other words, infinite series that even though they are infinite and we're constantly adding more each time, that they actually do have a sum. So as we start to look at those series, that they actually do sum to a particular constant value, even though we are infinitely adding more to them. So let's go ahead, let's take a look at what we have. So first, we know that every finite series has a sum. So for instance, if I look at a series, we put a bunch of plus signs between the terms. Well, if I have a limited number of terms, there will be a value that it sums to. It could be a very big value, but there will be a value that it sums up to. With an infinite series, though, what we see is we have a question. Can it actually have a sum? So I'm increasing the value, assuming all the terms are positive, and I keep adding these things. I'm increasing the value all the time, but is it possible that I'm increasing by a small enough amount that it is actually approaching some particular value and that it actually does have a sum? And so let's consider the situation and see if we can come up with an example where there is a sum. So let's consider, for instance, this series here. Very simple series. Notice the rule for each term is just that it's 1, doesn't matter what k is. So this is an infinite series here. So what this looks like, each term is 1. So we end up putting a bunch of pluses between 1s. And so as we can see, obviously, this infinite series has no sum. It continues to get larger and larger as I add more. There is no limit to it. So there we would say there's no sum. Now let's look at a different one. So this one, we're going to start at k of 0, and we're going to go -1 to the k power. And so what happens here is we see that we've got alternating positive and negative terms with a value of 1. So for instance, if I put 0 in there, -1 to the 0 is just 1. But then if I put 1 in there, I get -1. And then I put 2 in there, I get a +1. And it goes back and forth like that. And this one we'll actually see has no sum, but it's a little bit more difficult to see that it has no sum. So the way that we would look at this, if I look at one term, it's equal to 1. 2 terms is equal to 0. 3 terms would sum to 1 again. 4 terms would sum to 0. So what's happening is these sums, as I go up, are bouncing between 0 and 1, 0 and 1, 0 and 1. They're not particularly approaching any value, so that's also no sum. This one just keeps getting bigger and bigger and bigger. This one does not keep getting bigger and bigger and bigger, but it keeps bouncing between 0 and 1 each time, so it also has no sum. Now let's consider this one here, where we have 0.1 to the power of k. Well, if I start in with k of 0, my first term is 1. My next one is going to be 1 plus, and when I put a 1 there, it's going to be 0.1. And then I'm going to add 0.01. So as I keep going up by powers here, I get this series, which if I look at this one, what this one becomes, notice it becomes 1.1. Then I add the next one, 1.11, 1.111. So it becomes this 1.1 repeating. And it turns out that actually does have a defined mathematical value. 1.1 repeating is actually 10 over 9. Or you can think of it as 1 and 1/9. So that actually does have a sum. And so there is a particular value that this series adds up to. So even though it's infinite, even though I'm adding more and more to it each time, notice like for instance 1.11 is not 10 over 9. It's not until we include this infinite aspect that we get that it actually sums up to 10 over 9. But in this case, it does have a sum. So let's talk about classifying them. The term diverges means simply the series does not have a sum. So both of these with no sum are said to be divergent. They're divergent in different ways. This one continues to get bigger. And if I was to talk about the sum, I could say it approaches in a value of infinity. It just keeps getting bigger. This one does not approach an infinite value at all. It alternates as I go term by term between 0 and 1, but that's obviously not approaching a particular value, so it also would be said to diverge. Finally, this one here that does have a sum, we would say converges. So the definition of converges is the series does have a sum. In other words, as the infinite series goes off infinitely, it gets closer and closer to some particular value. So, how do we know if it converges? Well, there's a couple ways to check for convergence. The first thing we can do is look for the limit of partial sums. So partial sums are where, for instance, if we add up 5 terms, and we add up 6 terms, add up 7 terms, and we look at those sums and see if those sums are approaching some limit. So for instance, if the sum of one term expression is 1, the sum of 2 terms is 1.1, so this is looking at the partial sums of this series right here. The sum of 3 terms is 1.11. The sum of 4 terms, well, if we look at what's going to happen here to the limit of this, the limit of this is going to be 1.1 repeating. So if this limit here, if this sequence of partial sums here, so I'm looking now at just the sequence of 1, 1.1, 1.11, 1.111, and I look at that and I'm saying, okay, that is a sequence of partial sums there converges, then we can say the series converges. So that's one way to tell. The other way is to identify if it's geometric. So the most common way that we find convergent series is if the series itself is geometric. In other words, if there's a geometric rule for the sequence of numbers, then I can look at what the R is. And so I check for that R value. If the absolute value of R is less than 1, then the series converges. And if the absolute value of R is greater than or equal to 1, then it diverges. Okay. Conversely, if it doesn't converge, then it diverges. We could actually see that looking at the rule from a series from yesterday. Because if we look at this series here, so this is our general definition. So we have R less than 1. Okay, this we know it's going to converge. Then we look at this geometric series. So this is the definition of a geometric series. First term times R raised to the k minus 1 power when k begins with 1 here. This is our geometric. It actually converges to this. And this is from our definition. Remember, our sum for a geometric series was g to the first times 1 minus r to the n power. But if that r to the n, as n goes to infinity, that r to the n, if r is less than 1, goes to 0, so it becomes 1 minus 0, which is just going to be 1 minus 0 or 1, so it's just going to be that g of 1. So that comes from our formula that we had last time. So let's look at an example here. Actually, before I do that, I will show you. Let me quickly pull out. So this is me on the board making some notes for you to look at on the board. So what I would be doing here, you can ignore the stuff that's above it. I'm just pulling out that's other stuff that's on the board for a different class. So if we look at our definition of our sum going back to yesterday, so we look from yesterday at our sum of the geometric sequence, we know that in this case that when we have this sum k equal 1 to n, of g1 of r to the k minus 1 power, we know when we have this sum we define to be equal to g of 1 times 1 minus r to the n over 1 minus r. But if r is less than 1, then we know, so let's say we look at this n being infinite. So now what we see is that if n goes to infinity, and if r is less than 1, so this r here becomes less than 1 and n is going to infinity, this value here goes to 0, is what we see happening there. So eventually this value, as n gets bigger and bigger and bigger, this value goes to 0. So then this just becomes g1 times 1 minus 0, or g1 times 1, and it becomes just g1 over 1 minus r. So that's what we have here. Now, notice it is important to understand here, this g1 is the first value of the first term in our geometric series. Now, if k is 1, then it's easy to see that that's the value of our first term. But if we start this at k of 0 or k of 2 or something like that, when we go to enter it in this formula, our g1 has to be the value of the first term. So it's not just what's sitting out here. So for instance, if I start k of 0 here, and this looks different, or maybe my k starts at 2, then my g1 is not going to be the number sitting here. It's got to be the value I get when I plug in that first k value, and I get my first k value here. So let's take a look here at an example. And I'm missing my, here we go, So notice here, this is a little different. K is 3. So the G1 is not going to be 2/3. That can trip students up. If the K is 1, and I put a 1 in here, then I would get negative 1/4 to the 0. This would just end up being 1, and it would be 2/3. But because K is 3, first off, I know it converges because this R, the absolute value of that, is less than 1. So I know it converges. Now the question is, what does it converge to? So I'm going to use my formula. So it converges to, and I have to put in for my g of 1, what is the value of my first term? So when I put 3 in here, this becomes squared. So this becomes negative 1/4 squared, which would be 1/16. So when I take 1/16 times 2/3, I get 1/24. So that's my G1. That's the value of my first term, since when I plug in, that's what I get. And then this becomes 1 minus negative 1/4. So when I go ahead and do this, this becomes 1/24 divided by 5/4, which is 1/24 times 4/5, which this reduces down to 1/6. So this is going to be 1/30. And so if you started adding up these sums here, what you'll find is the first one, obviously the first term is 1/24, and as you go along, it's going to get closer and closer as you start adding additional terms to 1/30 as it goes. So it'll actually converge to 1/30. And on these, we need to see that you know how to evaluate them this way, but you can do it using your calculators as well. So if I was to pull out my calculator on this, and I'll show you how I can evaluate this on my calculator. So if I went here to calculate and I entered that series, so I would go here to my my template, which is right next to my number 9, and I would pick out my series template right here. So here's my series template, and I'm going to go ahead and I'm going to put I'll put K. So I have to find K equals 3, and I know I'm going to go to infinity, and my rule is going to be 2/3 times, and it's going to be negative, and it's 1/4. And that 1/4 is raised to the k minus 1 power. So I know it's going to be k minus 1 power like that. So now when I go ahead and I hit enter, notice we see that it does sum up to 1/30th. So it does converge like that, and we can see that. Now, you'll need to be able to do this without your calculator, but you also need to know how to enter it in your calculator and be able to find the sum of it that way. Okay, with that, your homework is going to be 23 through 30 and 43 through 45. Make sure you can do these both by hand. Well, you can go ahead if you need to, yeah, but by hand and by calculator both. So you need to be able to do it both ways. Make sure I see the work, knowing that you did it by hand, but then also you can use your calculator. You should be able to do it because sometimes you'll need to be able to use your calculator on big ones in order to get a sum quickly. So there's your homework assignment. Hope things are going well. We do have Zoom today. If you do need to ask questions, you can join our Zoom session at 12:45.